Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Welcome back to the second edition of Fundamentals of Solid Formulation webinar series. This is a 7-week webinar series with a webinar every Wednesday by a leading expert who understands your daily workflow and will share his or her real-world experience in supporting preclinical and clinical projects. So this webinar was started on April 7th and it'll end on May 19th. And for this second edition, we have experts from Gilead, Dr. Henry Morrison, and from Novartis, Dr. Sudhakar Garad, from Merck, Dr. Luca Isolino, from Millipore Sigma, Dr. Daniel Joseph Price, and from GSK, Dr. Luca Russo, from Vertex, Dr. Alesh Medek, and from Syngenta, Dr. Adam Keys. So these 7 experts will share their real-world experience in supporting preclinical and clinical projects. And as I mentioned, this 7-week webinar series is organized by XLPI and JSTAR Research. My name is Sivakumar Segran. I'm the Senior Director of Business Development at XLPI in Boston. XLPI is an algorithm-driven artificial intelligence-based pharmaceutical technology company with sites in Boston, Beijing, Shenzhen, and Shanghai. JSTAR Research is an innovative CRO based in New Jersey and is an independently managed subsidiary of Photon. Photon is a contract development and manufacturing organization based in China. The 3 organizations are strategic collaboration partners in pharmaceutical drug design and preclinical development programs. So before we move on to our webinar today, I just want to give you a brief recap of what happened in the last 4 weeks. Pretty much in April, we had 4 wonderful webinars given by Dr. Henry Morrison, Dr. Sudhakar Garad, Dr. Luca Isolino, and Dr. Daniel Joseph Price. So these 4 webinars are recorded and posted on our website. So if you click on the play button, then you'll be asked to fill out a form with your name and affiliation, and then you can watch the recordings. And as you can see here in this page, there's also the information about the Q&A sheet that is answered by the speakers. So pretty much the questions that were not answered during the live session are answered by the speakers and posted on the website along with the recordings. Right, so pretty much we want to make sure all the participants are heard. Whatever questions or feedback you have, we take that into consideration. So during today's session as well, please send in your questions and comments using the questions tab, and please indicate the slide number so that the speaker has an additional few minutes to take in more questions during the live session. So today we have Dr. Luca Russo from GSK. And Luca is a subject matter expert in crystallography, and he overlooks late-stage development assets within the material science group at GSK in Stevenage. Luca manages the single crystal XRD facility and provides structural insight into physical properties of crystalline forms in development. So today, Luca will present cases where crystallography has been used in combination with molecular modeling to address challenges in structure determination, as well as in understanding solid form properties and risk management. The title of the talk is Current Practice and Future Perspective in Crystallography for API Solid Form Risk Management. So without further ado, let me hand over control to our speaker, Dr. Luca Russo.
Hi, Shiva. Can I first of all check you can hear me okay and the video is coming through all right?
Yes, we can see your screen. Thank you so much.
Okay, that's fine. I'll just use a laser pointer. So good afternoon, morning, evening from myself as well to everyone. And thanks, Shiva, for the very kind introduction and inviting me to talk at this series. I have to say, I really enjoyed the 2021 and I'm for sure equally enjoying this year. So also a very well advertised event, which has quickly become very popular. In this talk, I will provide an overview on how crystallography is used at GSK in solid form risk management through the different stages of product development, from solid form selection through to formulation and process development and control. I think we can group tasks in crystallography workflows into two deeply related main groups. The first concerning acquisition of structural knowledge on solid forms, the second concerning rationalization and understanding of physical properties. I will present three recent examples we've been working on concerning acquisition of structural knowledge and finish with the last section on mechanical properties assessment that we are just starting implementing as an example of how we are using fundamental crystallographic knowledge to rationalize physical properties of our APIs in development. And during the talk, I will also try to highlight developing aspects of our workflows that more heavily rely on molecular modeling and are thus most likely to benefit from the breakthrough of CSP. So before the more technical part of the talk, I would like to give an overview of the most typical crystallography-based tasks in a pharmaceutical material science department. Traditionally, structural knowledge acquisition has very heavily relied on single crystal XRD structure determination, while physical properties rationalization has been typically addressed to form inversion screening and solid form characterization techniques such as GVS, DSC, TGA, etc. Over the last few years, we have been seeing an increasing use of molecular modeling, leading to the development on one hand of hybrid structure solution approaches, on the other of physical properties modeling tools. So from the exclusive use of single crystal XRD structure determination, we've seen increasing use of XRPD structure solution methods, hybrid Rietveld energy structure refinement, solid state NMR XRPD crystallography for cases where growth of single crystals for structure determination could not be easily achieved. As well as PDF for the characterization of amorphous phases. All these techniques heavily rely on molecular modeling of some sort. And at the same time, we have assisted to the progressive development of predictive tools for physical properties, for example, for modeling crystal morphology, mechanical properties, behavior of disordered solvent in channel solvates, or interaction of API with excipients. And I really think that the breakthrough of CSP can benefit and accelerate all of these tasks through increased availability of structural models and more robust validated modeling of supramolecular interactions, feeding into both structure solution methods and physical properties modeling. Now, CSP has been very nicely presented by Luca Iuzzolino 2 weeks ago, but I still wanted to take the chance to provide my personal view on this, as CSP is an important component of the crystallography strategy of our MatSci department. So starting with some high-level considerations, at the moment we are applying CSP to assets in late stages with the intention of increasing coverage towards early stages as we gain confidence in the results and assessments, though as things stand, cost could be an issue in this respect at the moment. Although there are expectations for CSP to gradually take over experimental form screens, we currently see the two very much complementary to each other, as limitations in experimental screens such as solubility and kinetic barriers may be addressed by CSP, and conversely risks related to space group and Z prime selection in crystal structure prediction may be mitigated by experimental knowledge. Definitely, CSP has a significant value in terms of establishing a reference structural database throughout the lifespan of the project, which is, in my opinion, still underestimated, for example, in terms of potential contribution to understanding of metastable forms and amorphous structure. I believe there is scope for developing focused or simplified protocols that Luca was also alluding to a couple of weeks ago. For example, for understanding of specific form transitions or for application of CSP in early stages. For example, a pre-candidate selection, which would require higher throughput workflows. And an important role, I believe, will also be played by the implementation of virtual databases and related analytical visualization tools, which will certainly help boosting the application of CSP outputs. Now, moving on to some more technical aspects, selection of sample space groups is crucial in terms of missing structures, in terms of risk of missing structures with unusual symmetry. Disorder often complicates the complexity of cases. From my experience, it can be rationalized where known to be present, but it's probably more problematic to predict in unknown structures. Overprediction can usually be addressed, I think, in terms of grouping closely related structures and highlighting the most significantly different ones for evaluation of potential risks. And overall, I would say this is an exciting, fast developing science. And while we are increasingly applying it to projects, ongoing CCDC blind challenges are there to remind us that there is still work to be done. And we should be careful in setting stakeholders' expectations at the right level. I will now move to the more technical part of the talk, starting with applications on the combined use of solid state NMR and XRPD for structure determination. I recall that Aleš Medek next week will be talking on solid state NMR, though applied to amorphous, so that should be quite interesting topic to follow up. So this is just one of the ways we can use to tackle crystal structure determination where, for whatever reason, we struggle to grow suitable single crystals. Here I will present the general workflow for this combined approach that can be used when a pure XRPD approach may be problematic due to data quality or complexity of the molecule. As first step, we need to define the 3D molecular structure for input into the XRPD structure solution step. At this stage, relevant structural knowledge, either from the CSD or from proprietary internal databases, is very useful to select the most appropriate likely conformations, for example, in presence of flexible rings. At the same time, the XRPD pattern can be indexed using supporting solid-state NMR evidence to confirm Z prime and help choosing the most likely space group. Having done this, we can move on to try and solve the structure, for example, by simulated annealing. This is where many problems would come to a dead end by a pure XRPD approach, either due to poor data or complexity of the molecule, and we may end up with a certain number of possible solutions, all with similar likelihood, for example, based on chi-square, and little to discriminate among them, even through refinement of the models. But this is where solid-state NMR can really help. The CASTEP package can be used to calculate chemical shieldings from the most likely structural models. The chemical shieldings can then be converted into chemical shifts and assessed against the experimental solid-state NMR spectrum of the target structure. And the assessment is then repeated after a geometry optimization, which should improve the agreement with solid-state NMR data. And at this point, we should be more confident in the selection of the structural model to progress to the final refinement step. Also worth mentioning that the procedure can be also applied to less problematic cases where we are more confident in the structural model to progress, though in presence of some questionable features which can be resolved by the custom geometry optimization and confirmed by the solid state NMR assessment and final refinement. I will now present an example where this workflow was successfully applied, in this case to improve a structural model obtained from XRPD structure solution, which presented suboptimal hydrogen bonding interactions. The compound in question is the development form of a dihydrate mesylate salt API. As it happens, a single crystal suitable for XRD structure determination could not be grown despite several efforts made. And some more information about the problem. XRPD indexing and solid state NMR were used to define unit cell and symmetry of the structure, which is orthorhombic in space group P212121 with set prime 1. The asymmetric unit content presents 23 degrees of freedom combined with 2 possible ring conformations. And XRPD capillary variable counting time data was collected in-house up to an angular resolution of 60 degrees to theta. A single crystal could later on be grown from a different batch, as it often happens, which confirmed the accuracy of the refined structure. As I mentioned, we could in this case identify with some confidence a convincing structural model out of the XRPD structure solution step and successfully refine it. Having said that, some hydrogen bonding distances and angles were slightly off range and clearly susceptible of improvement. I am showing here the refinement of the initial model, which does look quite good. And on the right, the consistency between calculated chemical shifts from the refined model and the experimentally measured ones from solid state NMR. Maybe 1 or 2 slight deviations can be observed, but overall this doesn't look too bad either. Still, the custom geometry optimization allowed us in this case to improve the consistency of the model with solid state NMR data, as highlighted by the reiteration of the solid state assessment step here. And the final refinement confirms that the improved model is still well consistent with XRPD data showing a slightly improved R factor. Beyond statistics of the solid state carbon-13 data, the solid state NMR of nitrogen-15 clearly describes the actual improvement of the structural model in terms of features of the molecule mostly affected and improved by the CASTEP optimization. The top spectrum in red is based on the CASTEP calculated chemical shieldings on the initial model from XRPD structure solution and following ritual refinement. Comparing it with the solid state experimental pattern in black at the bottom, we see some discrepancies. Especially for nitrogen-14 and nitrogen-18 highlighted in this detail of the parent API molecular structure. Overall, RMSD for spectrum comparison is 15 ppm. Following geometry optimization of the structure in CASTEP, we have recalculated the chemical shieldings on the new structural model and obtained the calculated solid state NMR trace here reported in green. We can see the improved agreement with experimental data, especially on the signals from nitrogen-14 and nitrogen-18, also accounted for by the much improved overall RMSD. And as mentioned in the previous slide, the final consistency with the XRPD data validates the CASTEP optimized model based on the slightly improved R factor and a rather acceptable RMSD on the refined atomic coordinates. Let's take now a closer look into the molecular, supramolecular aspects of the different structural models at the different steps of the process. So in this overlay, looking at the atomic color-coded model, we see the initial conformation around the protonated nitrogen, resulting in a long NHO interaction with the mesylate oxygen. After the following cast-step optimization, we observed the flip of the nitrogen, coming now closer to the mesylate oxygen of the model in magenta. And the blue model is from the final Rydberg refinement and looks in good agreement with the one obtained from the cast-step optimization step. So in conclusion, the low resolution of the in-house XRPD data was not allowing to correctly determine the conformation of the protonated nitrogen on the API cation, and eventually the single crystal structure, which could be determined later on, confirmed the accuracy of the final refined structural model. Moving now to the second example I am presenting. Here is a more challenging case for which we really struggle to unambiguously identify the most convincing structural model from the XRPD structure solution step. We are now talking about the mesylate salt of a larger parent API molecule with Z'2 and 40 degrees of freedom in the asymmetric unit for 10 possible conformer combinations in relation to the presence of two flexible rings. The table shows the possible combinations on one independent molecule labeled according to the conformation of the relevant substituted position. Several efforts, I should say, of growing single crystals were unsuccessful, invariably resulting in very fine needles, which proved unsuitable even for synchrotron data collection. We did try very hard, and in this case, with no luck so far. So, starting with the process for determining the structure, in defining the 3D input model for the XRPD structure solution step, likelihood of possible conformers was also assessed from structures of relevant solvates and hydrates, which were previously known, and where the different conformers were actually observed. So from the initial XRPD structure solution step, we obtained 10 candidate models reported in this table in relation to the 10 possible conformer combinations. And from these three truly unique ones were identified based on supramolecular environments of the hydrogen bonding functions. Of these three, MO3 as one independent molecule with both ring A and ring B axial, and the other with ring A equatorial and ring B axial. On the other hand, solution M10 has both independent molecules with ring A equatorial and ring B axial. And finally, the MO1 solution has both independent molecules with both ring A and ring B axial. And at this stage, it was not possible to discriminate among these three solutions based on XRPD only. So as next step, calculation of chemical shieldings in cast-step was used to simulate solid state NMR spectra for each of the three likely structure solutions, M10, MO3, and MO1. And M10 with both independent molecules having ring A axial and ring B equatorial was identified as the most likely solution over the other two and progressed into final refinement based on the solid state NMR assessment. And you can see the related solid state NMR trace in green is the closest match to the experimental solid state NMR spectrum at the top. So the R factor from the final RIT12 refinement of the M10 solution looks acceptable, though the RMSD is a bit higher than what we would ideally like. Considering the low packing coefficient of the structure, we concluded that a model disorder was likely to be responsible for the observed discrepancy between the CASTEP optimized and RIT12 refined model. But I should say, to date, this is still the best structural model we could obtain for this crystalline form. I will now move on to the third example I'm presenting today, where RIT12 refinement with an energy function was used in combination with molecular modeling to provide structural knowledge and solvation behavior rationalization on a transient non-stoichiometric solvate, which is produced upon drying of the API in the crystallization stage. And in this slide, I will describe a general workflow which can be used in similar challenging scenarios, that is to target transient non-stoichiometric solvate structures. Given the transient nature of the target form, we must rely in this case on the availability of an isostructural model from either the final development form of the dried API or from an isostructural solvate as a prerequisite. Once we have this, as a first step, we remove the solvent from the structural framework of the related form. Next, we transfer the dry structure in the unit cell of the target transient form, which we must have previously determined by XRPD indexing. XRPD indexing is, of course, assumed to confirm that the known and target forms are isostructural. We can then simulate the absorption of solvent molecules in the framework, aiming at the solvent loading suggested by experimental evidence such as GBS and consistent with the estimated void space. And we can finally refine the obtained model against the XRPD pattern. Typically, this would be a low resolution one. In these cases, data quality would not usually support the full RIT12 refinement, but an energy function in the form of force fields can be used as a restraint to better control the free refinement against XRPD data. And this is an example where we have recently applied this workflow. The intermediate form rapidly desolvating to yield the target API development form was observed and characterized in the wet cake. And in order to try and gain some structural mechanistic understanding on the drying process, we collected a variable counting time XRPD capillary data, sealing the slurry in a capillary for data collection. GVS, using the dry API development form as input, was suggesting a 1.5 to 1 solvent to API ratio involving the process solvent, that is ethyl acetate. And from indexing of the XRPD pattern, we could link this intermediate to a previously known methyl THF solvate, the structure of which was previously determined by single crystal XRD. And I should mention that in the methyl THF solvate crystal structure, from analysis of the Fourier difference map, a 1-to-1 API solvent stoichiometry could be estimated, but the methyl THF solvent was eventually removed by means of the squeeze routine in Platon due to disorder. Following on from the previous slide, the previously known methyl THF solvate and the suggested isostructural ethyl acetate solvate have very similar unit cell metrics with individual axis length variations within 5%, and both crystallize in space group C2. Based on the unit cell similarity, we could transfer the dry structural framework from the methyl THF structure into the unit cell of the target ethyl acetate solvate. In the void distribution analysis, a 16% void space was estimated by Mercury in the dry framework structure, presenting two symmetry-independent channels. And based on the 18 cubic angstroms rule, the void space could, in theory, account for the presence of up to 12 molecules of solvent in the unit cell, corresponding to the experimentally suggested 1.5 to 1 solvent to API ratio. As a next step, ethyl acetate solvent loading in the dry framework was attempted using the sorption module in Material Studio. A configurationally biased approach was used to best handle the conformational flexibility of the solvent molecule and achieve the most efficient packing of solvent in the channels. And the compass 2 force field was used in the simulation. Although the 1.5 to 1 experimentally suggested solvent to API loading ratio was attempted in several simulations, it could never be achieved, and the 1-to-1 loading ratio was the highest achieved, leaving a residual estimated void space of about 300 cubic angstroms. It's interesting to observe as an output of the simulation the bimodal distribution of the sorption energy, presumably corresponding to the solvent uptake in the two symmetry-independent channels in which the solvent seems to adopt a different conformation. And finally, the modeled 1-to-1 solvent was refined against the variable counting time XRPD pattern using the compass 2 force field as a restraining energy function. The refinement is clearly affected by the low quality of the XRPD data, which was collected on a slurry and as such very noisy and also requiring a rather problematic background removal. Also, limitations on the solvent modeling must be highlighted, as the solvent is very likely to be disordered, thus making the geometry optimization quite problematic. Nonetheless, the refinement can be considered satisfactory in confirming the nature of the intermediate transient solvate, and most importantly, shedding some light on this form transition. Now, in the final part of the talk, I will present a case study from an ongoing effort towards a comprehensive mechanical properties assessment based on fundamental crystallographic knowledge. There is a good number of recent publications on mechanical properties prediction. One of the most active authors in the field being Jerry Heng, who was presenting at this seminar series just last year. In general, several examples can be found in the literature on the rationalization of mechanical properties, ranging from more qualitative approaches, typically based on the observation of slip planes in the crystal structure, to more numerical ones based on the calculation of attachment energies or elastic properties from molecular modeling. As I mentioned, this is an ongoing effort, as there is still some work to be done in terms of identifying the descriptors and calculated properties most relevant to our processes, and also in terms of how fundamental particle properties translate into bulk properties. So, building upon published case studies, we've been gathering all the available crystallographic descriptors deemed to be relevant to mechanical properties on a number of drug substances in development. I will now go through such descriptors collected on an API that we have included in this ongoing internal pilot study. This is a neutral API developed as free acid, showing a rather high density and good packing in absence of significant voids, suggesting we have a highly cohesive drug substance to start with. Next indicator, consider this thermal expansion. As part of our single crystal structure determination workflow, we routinely collect full datasets at 150 Kelvin and double check the unit cell at room temperature for possible transitions later on. This provides us, among other things, a useful information on the thermal expansion behavior of our APIs. In this case, we can, for example, observe a very anisotropic behavior as most of the expansion happens along the crystallographic B-axis, suggesting the respective compression direction as the most compliant one. Keeping in mind potential phase transitions is definitely an important point when considering how our API may react under stress. In this case, we knew of a closely related polymorph with Z'2. In general, structures of closely related forms may be also used to highlight potential routes to plastic deformation or breakage. Hydrogen bonding connectivity is also a useful indicator to identify potentially less compliant directions in the structure. In this case, we observe a 1D connectivity along the crystallographic A-axis. And finally, evaluation of slip planes. No slip plane could be identified in this case, and based on this, we can expect steric hindrance as a limiting factor towards slippage along most weakly bound planes. In the absence of clear slip planes in the structure, rugosity is a useful descriptor accounting for steric hindrance towards slippage along the different planes. This cartoon describes calculated rugosities for the most significant directions in relation to the main crystal faces based on the BFDH crystal morphology model. And beyond this, morphology modeling helps linking the different planes and directions in the structure to the geometry of the crystalline particles, allowing to predict their relative orientation towards the applied mechanical stress in our processes. Most importantly, energy-based morphology modeling provides a quantitative estimate of the attachment energies across different planes in the structure. And here is the overview of the growth morphology modeling for our API development form crystal structure at two different levels of theory. We usually start with a force field based model for an initial quick assessment, which we then validate with a more accurate DFT based model. In this case, the two models are in good agreement, both indicating the AB plane perpendicular to the 001 direction as the weak plane, followed by the plane perpendicular to the 011 direction, approximately parallel to the AC plane. And while morphology modeling is very useful for providing attachment energies and confirming the relative orientation of crystallographic planes under stress, assessment of preferred orientation in XRPD patterns is a very effective tool to monitor preferential breakage direction of the crystallites in a powder, for example, during milling. In the case of our study API, PO assessment confirms preferential breakage along the plane perpendicular to the 011 direction. That is the plane with the second lowest attachment energy, as we observed in the previous slide. This is somehow not what we would have expected in first place, but can be rationalized, I think, when considered in combination with the rugosity values of the two planes. So trying to summarize all the most significant gathered indicators along with calculated elastic properties in a comprehensive assessment, we have the attachment energies based on which slippage breakage is expected to happen along the AB crystallographic plane. And in accordance to this, it is also predicted to be the experimental main phase. Rugosity, based on which slippage along the AB plane, on the other hand, appears prevented in relation to the high degree of interdigitation occurring across the planes. And Young's modulus and thermal expansion calculated values, both suggesting the B direction as the most compliant one. In conclusion, despite having only the second lowest attachment energy, the AC plane is identified as the preferred breakage direction in accordance with the favorable rugosity compared to the AB plane with the lowest attachment energy. And in terms of assessing, on the other hand, compressibility, thermal expansion and Young's modulus seem the most relevant indicators, though we are also looking at hardness using AFM nanoindentation as a supporting validating tool. Bulk average parameters provide a simple way of ranking drug substances in terms of expected compressibility behavior, though they may be not applicable in the case of extremely anisotropic morphologies. In the case of our API, the bulk modulus is 8.7, 10.9 gigapascal, reporting either the Royce or Voigt averaged value, which suggests a similar behavior to paracetamol form 1, for which very similar values, experimental values, are reported in the literature. And with this, I would like to finish with some acknowledgements. First, to GSK colleagues from Solid State NMR, Tran, and Andrew for obviously contributing to the Solid State NMR XRPD crystallography workflow. Several people, I should say, from materials science department, but in particular Spurti, Amy, Stephanie, and Mark for providing project management and experimental support. Parind from process engineering and analytics for driving the mechanical properties workflow development. Our external collaborators from crystallographics, Norman and Kenneth Shankland for XRPD structure solution determination, Bill Clegg and Mike Probert from Newcastle University for single crystal structure determination, and finally Crystal Pi, in particular Shiva for organizing this series and inviting me to speak, and finally you all for kind attention. Thank you.
Thank you, Luca.
I'm now ready for questions. Yeah.
Yes. Thank you. Thank you so much, Luca, for the wonderful presentation. A lot of valuable insights into solid state NMR and mechanical properties and how they are applicable for solid formulations. So let's move on to the Q&A session. So the first question is related to slide 11. And the question is, did you compare the energy minimized structure with Rietveld structure, and do they agree well?
Sorry, I'm just navigating to slide 11. Just a second.
Mm-hmm. Sure.
Okay, you should see.
So the question is, did you compare the energy minimized structure with Rietveld structure, and do they agree well?
Yes, I did, and I think it was yes. That's what is summarized by this RMSD value. So it's basically the it relates to the overlay of the Rietveld refined structure with the CASTEP geometry optimized structure. So we consider this value acceptable.
Okay. Staying on this slide, slide 12, is the calculated N15 NMR is specific to solid state?
Yes, it is from. Yes, it's from the solid state structure. Yeah. Yeah, it's
okay.
yeah, it comes from the XRPD structure solution model, the red one. Yeah.
Mm-hmm. Okay. The next question is, how did you locate hydrogen atoms?
Oh, we are not locating hydrogen atoms in this case. I mean, not generally speaking, not when we solve structures from powders. They are fixed in the model. We mostly refine translations of the molecular components and torsion angles and conformations of the rings, but in general, not bond lengths.
Okay. Next is a very general question. What are the usual strategies used for growing single crystals by GSK?
Oh, I'm not sure we really have a strategy. I think we rely on the green thumbs in growing crystals from our particle scientists or chemists, depending on the stage at which the compound is in research, discovery, or development. Probably there is more automation at the moment in protein crystallography, but we are actually looking into this.
Okay, so let's move on to slide 20.
Yeah.
Yes.
Should see it now.
Yes. So the question is, does capillary VCT offer better XRPD than normal holders for acquiring XRPD?
Sorry, I missed something from the previous part. Can you repeat it?
Yes, sure. Does capillary VCT offer better XRPD than normal holders for acquiring XRPD?
Yes, it is definitely the preferred solution when you want to try and solve the crystal structure. I mean, there are different applications for which you would measure a powder pattern, but definitely for structure solution, capillary data collection is highly recommended, also for address preferred orientation. And VCT, the variable counting time is collection strategy is useful to get signal as high angle as possible. Yeah, for better resolution of the structure.
Okay. Let's move on to the next slide, 21. The question is, can a desolvated solvate be differentiated from the solvate form?
Good question. I assume the question is implies based on powder diffraction. I think the answer is yes, because I've actually tried different structural models, different stoichiometries for the solvate. For example, I've tried the 0.5 and the 1-to-1 stoichiometry, and I could see a measurable improvement in the R factor with the 1-to-1 stoichiometry. So yeah, I mean, I can confirm that based on refinement, one could prefer the 1-to-1 stoichiometry over the 0.5-to-1 stoichiometry.
Okay. Next question is, how would you introduce defects in the models for assessment of the mechanical properties?
Oh, that's that's a very good question, though. I don't think I'm able to answer. Yeah,
Okay.
I don't have an answer at this stage. There may be something in the literature, but I guess that is a big challenge. Yeah, it may be that defects would account for the good part of mechanical properties in some cases. Yeah, I think they're hard to model.
Okay. The next question is related to slide 29.
Yeah.
So I would also like to thank the participants for putting in the slide numbers. It's really helpful. So I encourage everybody to do that while putting in the questions. So
yeah,
moving on to
yeah, they help.
So moving on to slide 29, the question is, what is PO evaluation?
Sorry, yeah, try to avoid abbreviations. That's preferred orientation. So in this case, there's the patterns at the bottom. Sorry, I rushed through this slide for sake of time, but the patterns at the bottom are calculated patterns from the single crystal structure. The pattern in magenta has some simulated preferred orientation, essentially along this direction, highlighted by these planes in red, and you know, this confirms that looking at the Miller indices of the reflections, that the actual preferred orientation is along this direction parallel to these planes.
Okay. The next question is, what are the techniques to differentiate salt from co-crystal?
Oh, yeah, that's a good one as well. Well, I have to say we haven't got too many co-crystals in development at the moment. In general, it's difficult to differentiate between salts and co-crystals from based on X-rays, although you can when you have a very high quality single crystal structure. Otherwise, you would rely on neutron at central facilities. Yeah, I don't think NMR is always conclusive in assessing that. Yeah, so in general, either you have a very high quality single crystal structure where you can locate the hydrogen, or yeah, you would need a neutron data collection.
Okay, let's move on to the next slide, 30. How do you calculate the Young's modulus, simulation or experimentally, using a specific phase of the crystal?
Oh, these are calculated values from the FT in CASTEP. Yeah. But yeah, we are also looking at experimental supporting evidence, typically from AFM. I think the question was alluding to that. And in that case, yeah, the challenge is to measure on the different phases, which are not always accessible experimentally.
Okay. The next question is, how can data science or machine learning be applied to this problem? Are there any raw data results that lead to any bottlenecks?
I'm not sure I can answer to this question. I mean, at the moment we are just trying to gather this type of qualitative, quantitative information from our structural databases, and I mean, once we we can better define our workflow, then probably we can more systematically harvest data and try to inform some models. But yeah,
okay.
I wouldn't know at the moment.
Time for two more questions. So the next question is pretty general. So the audience would like to know how decisions are made at GSK, how the data is consumed across different teams, since you presented different properties and the impact on solid formulations. So how is the data consumed, and how do you arrive at decisions to select a stable solid form?
Yeah, it's depends a lot on cases, but in general, it's quite open environment. It's nice to work in here in the sense that everyone talks to everyone, and there are some established workflows. We have some reviews at certain points in development, some technical reviews, especially useful within our ChemDev department to discuss this kind of issues related to solid form. But in general, there are work stream leads as well as department leads, like we can have one in material science, and they they keep up with the project data acquisition at different levels, and then there are these reviews where people can we seek endorsement at higher level, we present the data, and we discuss problems.
Okay. The last question for today's session, it comes from an aspiring grad student specializing in crystallography. So want to know what skill sets should they develop before entering into the pharmaceutical industry as a crystallographer?
I would say if you're a crystallographer, try to be the best crystallographer you can, definitely. I mean, there are I mean, the best way I could think of is still measuring. Yeah, I've learned a lot just measuring either in-house or at central facilities, and there are really so many resources available nowadays, also online. So many seminar series, mostly free. So yeah, that's. Yeah, I think one should focus on technical learning, and then once you get into the company, that there's room to learn about pharmaceutical development science. Yeah.
Excellent. Okay, so that pretty much
I guess
concludes.
This was the last answer. So I'll just thank again the audience and you, Shiva and Crystal Pi, for organizing this great series.
Thank you so much, Luca. We really appreciate your contribution to this 7-week webinar series. So thank you to all the participants for joining in today. And before we sign off today, I just want to alert you about what's coming up next week. It's Dr. Alesh Medic from Vertex, who's going to talk about application of 15N solid-state NMR to differentiate and quantify different API amorphous phases in complex tablet formation. Alesh specializes in solid-state characterization of pharmaceutical solids with special interest in characterization of disorders. At Pfizer, Alesh built up global solid-state NMR capabilities and developed multitude of new solid-state NMR pharmaceutical applications. And at Vertex, currently, Alesh's interest expanded from solid-state NMR to all solid-state characterization techniques. So looking forward to Alesh's presentation next week. And I'd like to thank all the participants today for signing in and listening to Dr. Luca Russo's presentation today. So please send in your comments and questions to sivakumar.segren@excelpi.com. As I always mentioned before, it's all about you, not about the organizers. So please send in your comments and questions, and that will really be helpful for us to pick on the topics and the speakers for the third edition in 2022. So we're looking forward to hearing from you, and some of you we already reached out to, so to hear your feedback and comments. So please let us know, and looking forward to seeing you next week. Until then, take care, stay safe, and stay healthy. Thank you so much.